In this video, you're going to learn how sets have extremely fast membership checking and much faster than lists. So what we're going to do here is compare list and set membership checking. And in this cell down here, we're going to create a list and a set that have the same 1 million integers. I'm going to execute this. Here n is 1 million. We're first going to create a range object and then pass it to the set constructor. That creates a set of 1 million numbers. And then also with the list constructor, that'll create the same exact values, but in a different data structure, a list. So we are then going to use this %time magic function in order to compare the time. So this is something new. I'm going to bring it up in just a second. But first, I just want to make sure that we know how to do membership checking, which we just did. So first I'll compare this. I'll check whether some number like 900,000 is in this list. That is true. And then membership checking for a set happens in the same way. That is true. Now, there is this %time magic function that's available only in Jupyter Notebooks. So you need to realize that this will not work in a Python file. It only works inside of this Jupyter Notebook. It's just a little enhancement that the notebook provides in order for you to time code. So even though these operations, let me run them again, happen instantaneously on my machine, they do have some amount of time. You can measure it in milliseconds or microseconds, nanoseconds, whatever it is, it's very fast, but it is still measurable. And we want to measure this time. And the way to easily do this is with this %time magic function. So it's called a magic function just because it does some kind of, it's basically magic. It's just a short little function. And in this instance, it will calculate the time of execution. All right. And this is important because some applications are very dependent on having a calculation happen, very as fast as possible. Even though this particular, application over here happens instantaneously, there could be some times when it will amount to actual real world seconds or minutes or even hours. And then, so that can have an actual pretty large impact. And so a lot of times we do care about, even though computers are very fast these days, we still care about the performance. So you can just imagine like playing games or, being on the internet, making trades, in the stock market where really all this little time can really make a big difference. Okay, so what I'm going to do here, I'm just going to copy this. And the way you can time any single line of code like this. You just put %time in front of it. And if you execute this, it'll give you multiple different times. But what we care about is the wall time. This is the actual time it is taken to complete this, like in human time. And let's also see how much time it is with a set. So let me explain this first. So the wall time is in ms. This is milliseconds. So this is 1/1000th of a second. So 1,000 of these will equal 1 second. You can see this is just 17. So it's very, very fast. It's not noticeable to the human eye. Let's see this one. And this also looks like just about 17. But if you take a closer look, it is the Greek letter mu. This stands for microseconds. This is 1/1,000,000th of a second. So it takes 1 million of these to equal 1 second. So this is a much faster operation with a set. In fact, it is almost exactly 1,000 times faster. So that is very cool. And let me show you one that will not be as different. So let's check if the number 1 is in a list. That took 10 microseconds. And I'll check one over here that took almost about the same as before, about 19 microseconds. So now they're very comparable. In fact, the list was a little bit faster than the set. And the reason for this is the way that lists and sets are constructed, behind the scenes. So they are different data structures, and the way they are set up is the way the data is stored is very differently. So with a list, what happens is Python will go through each value in the list one at a time. So it checks one at a time starting at the left. So this list right here actually begins at 0. So 1 is the second item in the list. Once it finds out whether it's in here, then it doesn't have to check all of the other numbers. It can stop checking. So this only does 2 checks. and then it doesn't answer. When we did 900,000, well, it checked 900,000 integers. So it tested equality with 900,000, and that's why it took so much longer, like more than 1,000 times longer. With a set, there is a special way that is set up for determining whether an item is in the set. It's called a hash table, and all of the numbers take approximately the same amount of time. So it doesn't matter if I'm using the first number, and there's no first number in a set, or the last number. And again, this is not actually the actual last number. They will all take around the same. So it looks like maybe, somewhere around 20 to 30 milliseconds. Of course, I'm recording this, so I might have different times, but essentially it's not going to deviate too much. And let's just pick some number at random so you can see this. They should be, somewhere around 10 microseconds. Let's just choose a couple more. This, for list, it will depend where in the list the item is located. So it's in the beginning, it's at the end. The reason I made that's why I had to make the list so large of 1 million numbers so you could see a difference. If I only did it of 10 numbers, you wouldn't really see a difference because it's so fast. But with 1 million, you do see a significant difference. All right, so all that to say is that whenever you're checking an item, whether it's an element or a member of the set using this in operator, it will happen very, very fast, and it will do so for all of the elements. It doesn't matter really too much how many elements there are, or how long this integer is. It doesn't really matter. It'll still happen very, very fast.